who will talk about gradient tomography of jet quenching in heavy ion collisions. So let's get the show on the road.
Okay. Well, thank you very much. I think this is the best we can do to meet each other online. So my talk today is about gradient tomography of jet quenching in heavy ion collisions. So this is something new idea we came up over the last year, and it's just been published with this archive papers here. My collaborator on this project with Yayun, her, and Longgang Pan. So this is unlike my talk, I will give a very brief introduction, and then I will illustrate the problem in a solvable Boltzmann equation, and then I will illustrate this problem again in the more sophisticated simulation using linear Boltzmann transport. And then finally, I will talk about how we can use this gradient tomography to study, for example, gamma jet production, and then finally with a summary. So we all know that when you have jet propagate through the medium and through multiple interaction, and this iconal approximation, if you assume that your quark propagate along a straight line, you neglect the transverse diffusion in this case, and then you can write out the scattering amplitude as a Wilson line along their trajectory, and then if you square it, and then here you get the transverse momentum dependence of this quark propagation as it goes through the medium. And if you do, for example, do transverse expansion, if you do Taylor expansion of this variable with respect to the transverse coordinate, and in particular, and you have a series of expansions, and if you neglect the correlation of multiple gluon correlation beyond 2, for example, or if you think that all higher order correlations can be expressed as a product of the two field correlation, and this is equivalent to what people call dipole approximation at short distance. And you can find out that this distribution, transverse momentum distribution, in fact satisfy a diffusion equation, and with the coefficient defined as what we know as the jet transport coefficients, and this is you find out this is proportional to glue density distribution inside your medium. So this is why we always say that by jet quenching, if you probe the jet transport property or coefficient of the medium, you are actually looking at the gluonic properties of the medium. So in a static medium, this actually has this diffusion equation has a solution, and this is well known. This is just the Gaussian distribution, and we know that this glue transport, this jet transport coefficients enters both elastic and radiate energy loss. And for example, this elastic energy loss is per unit length is direct proportional to Q hat, and also the radiative energy loss in many different forms, all proportional to the Q hat. And here I only listed this result in high twist approach. This is the equivalent to the leading opacity expansion, for example, in GOV approach. So if you calculate for example, the total the energy loss both from elastic and radiative processes here, and you can calculate the energy loss distribution. This is the equivalently what we call induced splitting function. with this induced splitting function, and then you calculate if a jet is going to fragment, and then its fragmentation function will be modified. And you can express this modified fragmentation function as a convolution of the vacuum fragmentation function with this induced medium splitting. And with this modified fragmentation function, you can, of course, calculate the medium modified high PD hadron production in this leading order form of collinear factorized jet high PD hadron production process. Of course, because of this energy loss, and then which enters into the induced splitting function, and that leads to modification of medium of the fragmentation function, and this will simply lead to suppression of leading hadrons. And this is the reason why we argue that by studying the suppression of leading hadron, you can have indirect access to the value of the Q hat along the trajectory of parton propagation. And within the jet collaboration, we actually did this systematic analysis by looking at leading hadron suppression at both RIG and LAC, and with different model implementations of the energy loss. And then we conclude that one can actually extract the Q hat, in particular the initial value of the Q hat at the center of the most central interaction here. And then this is at both LHC energy and 2 RIC energies here. And this is, of course, is very large comparing to what you can expect from a cold nuclear matter, which is about 100 times smaller. And within this, of course, extractor, we assume that the space-time evolution is given by the underlying hydrodynamics. And that's the basic assumption here. So, okay, if you examine this propagation, let's go back to the basic for a moment. So according to this Boltzmann equation, if I neglect the inelastic scattering just for a moment, and also if you can consider the drag term coming from the elastic energy loss, and you find out that the Boltzmann equation can be written very similar to this diffusion equation, except now we are looking at both the spatial and momentum diffusion according to this, what I call a drift diffusion equation here. And surprisingly, actually, we actually trying to, you can solve this equation analytically, especially giving an initial distribution of point-like particle. And this analytic solution has a very, very interesting form, okay? And we actually looked around trying to find out whether there's any such analytic solution for this type of Boltzmann equation. And I think we couldn't find any, but this is a very nice analytic solution for this. And you find out, in addition to this momentum diffusion, as we saw before, in a spatial distribution, you also have a drift. And inversely, you can rewrite this in terms of diffusion in the momentum space, and then you also have a drift term in momentum. So, and this essentially gives you a correlation between the momentum diffusion and the coordinate propagation. So, if you, for example, if you integrate over the space and only look at the transverse momentum, you end up just normal diffusion, expression in momentum space. And conversely, if you integrate over all momentum, and just look at the coordinate space. You have this transverse. You have the transverse diffusion solution. So, and that is in a static limit, static medium. For this kind of Boltzmann equation in a non-uniform medium, and then is not possible. At least we're trying to find any analytical solution for even simpler momentum spatial non-uniform medium, and we couldn't do it. So finally, we have to use the brute force. We use the Monte Carlo simulation to solve this equation, or also we use just use the brute force to solve this partial differential equation, and then this gives us a confidence that our numerical solution is right. Both of them, for example, in this curve, the histogram I think is the numerical solution. The dotted line is just Monte Carlo simulation. They agree quite well. So we set up an example of this non-uniform medium in such a simple toy model here, and with in the transverse direction, we have this sort of elliptic shape. So you can change the parameter of ax and ny to change your shape of your transverse medium, the size of the medium. And then one of the tau quantity just to simply simulate the longitudinal expansion of your medium. And then what we are doing, if you look at, just like for example, if you look at the gamma jet problem, if you select your gamma, you know the direction, you know the angle between your direct photon and the event plan or event plan here, and then you can define a quantity. What is the anisotropy between upper plan and low plan. And you can imagine that if my initial production point is away from the center, as the jet propagate, the transverse gradients, the transverse gradient of the medium reflected in Q hat will have a momentum symmetry for this final jet momentum distribution. So here we define this anisotropy as here you can use the simple case, you take a sign and just looking at the symmetry between up and low respect to the event plan here. And indeed you can see this asymmetry indeed depends on the position, the transverse position of the y here. If your initial position is on the upper level, the anisotropy, you have more particle flowing in the upper direction. Consequently, if your initial position is in the low plan here, the transverse diffusion, of course, will give you momentum anisotropy. You have more particles going downwards. And this anisotropy, of course, increases with your medium size, and also it depends on which direction you go. For example, if you go this direction, outer plan, the gradients along this direction here is smaller than in this direction. So you certainly get a larger momentum anisotropy compared to this one. And in addition, also we look at if you look at the total propagation length here, and then indeed the anisotropy increases as you increase the total propagation length.
So we have 1 minute left.
Okay, so I will go. I will not show this picture here. So finally, we look into the linear Boltzmann transport equation. So I think this Boltzmann transport equation, we simply use both have elastic and radiated process, and we use also a 3D hydro viscous hydrodynamic provided for the bulk evolution. So here in this full simulation, you will have radiated correction, you will have multiple scattering here. I'm not going to tell you about all of these wonderful things that you can do with this LBT model compared to single jet. For example, gamma jet, both for the asymmetry and the modification of translation function here. And so here is final result with this simulation here. I have 5 minutes, right?
No.
Oh, you did. I didn't hear the warning. I'm sorry.
Okay.
Okay. So here is a full simulation.
Need to wrap up.
Indeed, and you can see that. Then here we define the energy asymmetry here instead of multiplicity. Indeed, the asymmetry is will have a strong correlation with the initial position here. So finally, we look at the full simulation. Suppose we look at the jet initial production point by triggering, for example, the value of the transverse energy asymmetry here. If you have no symmetry, all the production points happens to be centered in the center, while if you have positive asymmetry, it is biased on the upper plane, and also towards this direction here. If it is negative, it is biased towards downward. And similarly, if you change the orientation direction, and instead of in plane and out plane, you also get a very different initial distribution. So this actually, we think this is we using this gradient tomography by triggering on this transverse asymmetry with respect to the jet propagation direction, for example, by using gamma trigger, for example, dihedron trigger, we think you can actually localize the initial production point. And then with this localized initial production point, you can do many studies. So here, just one example, for example, you can look at length dependence of energy loss, for example. And then by doing so, you can also do more detailed analysis of your data with this trigger. And hopefully you can also get a spatial distribution of the Q-hat distribution in the heavy ion interactions. Okay, I will stop here.
Okay, thank you. So
Somebody buying coffee for me?
I didn't see any questions in the chat yet. Oh, there's one from Matt Sivert. Hang on a second. On slide 9, you can go there. You write the medium-induced, slide 9, the medium-induced radiation spectrum you use for LBT. Does the medium motion only affect the spectrum through the Eikenel factor, p.u?
The flow velocity, yes. Yeah, if you and there the p.u essentially the well, in fact, what we do in the actual numerical implementation, we transform to the co-moment frame, and then we do the elastic scattering and induced radiation, and then we transform back into the lab frame and do the next propagation. So that's what we numerically implementation of this formula.
Okay, I think we unfortunately only have time for one more question. Ivan Vitev is asking whether this suggestion is different than other studies of correlations with triggers and event plane.
The difference what?
Is the suggestion different than other studies of correlations with triggers and event plane?
Well, I think it's different because in this case, by looking at the symmetry, you can, as I said, you can sort of localize the initial production point. I want to go back to the last slides, and you can, I know that you can look at like jet and you can look at using the Jet V2 so that you can have a selection of the average length, propagation length. But in this case, this is more than that. This is more than the total length. You can actually pinpoint where it comes from instead of the average propagation length by triggering on this transverse asymmetry we define for this what we call the gradient tomography. You have to combine this with other measurement, for example.
Okay, unfortunately, I think we have to move on to the next talk. So thanks, Xin-Nian again. Can you stop sharing and
Sure.
Sharon, can you